Hello everyone, my name is Hossein Jodeiri. I'm a fourth-year PhD candidate at Laurentian University. In this meeting, I'll be talking about the 2.5-dimensional multifocusing imaging method that we developed for critical line seismic surveys. Also, I'll present its application on the larger Lake R2 seismic line. This research was conducted under the supervision of Dr. Negizadeh, Dr. Smith, and Dr. Yilmaz. The Metallers project collected larger lake seismic data along the existing crooked roadway over a hard rock setting. The crookedness of the survey line, in addition to complex subsurface geology with steeply dipping layers and low contrast impedances, all could negatively affect the resolution of the resulting images, and also hamper the application of the conventional seismic imaging method. Therefore, our main goal is to generate high-resolution seismic images and improving the accuracy of the velocity model. In this research, we developed a novel multifocusing algorithm for crooked line seismic data, which can have the ability to address all these issues. Let's quickly review theoretical and technical challenges imposed by crooked line survey geometry. The schematic figure shows a crooked line seismic survey. The survey line is shown in blue over here. Green and magenta dots represent midpoint locations and reflection points for the entire survey respectively. All these black ray paths are for the specific supergather shown in red here that contribute to image this small part of the reflector. I mean, during processing, we should focus all these reflections at the correct location that represents this part of the reflector in the resulting images. This transparent white plane is the desired imaging plane in the conventional processing method. However, in the crooked line seismic survey, ray paths between source and receiver take shortcuts passing around, behind or in front of this plane. For comparison, I superimpose these black reflections data for the same location collected with a straight line survey. Comparing these two reflection data shows how the crooked line can affect recorded data. In summary, irregular distribution of source and receivers along a crooked profile disperses the midpoint locations from the processing line, which violates the assumption of a straight survey line assumed in the 2D imaging methods, and also results in considerable time variant delay among reflections, which is shown in here, a low and variable fold coverage, and could defocus and deform reflections, particularly from reflections with a cross-tip component. Up to this slide, we understood the problems and why we need to develop a new method. This figure shows ray geometry for a crooked line survey configuration above a 3D dipping reflector with both inline and cross-line dip components. The black solid and dashed lines are the survey and processing lines respectively. The solid blue line is the reflection ray path, which is generated by a randomly located source on the crooked profile, intersects the central plane at point F, hits the dipping reflector at point O, arriving back to the surface, and is recorded by the receiver R. Snell's law indicates that the incident and reflected rays are coplanar with the reflector normal. Therefore, we can treat each pair of source and receiver as a 2D seismic survey acquired in a specific direction. Therefore, we need to derive functions that connect the wavefront parameters to apparent dips. Finally, we can decompose the derived apparent dips into inline and cross-line dip components. This is an example of supergather before and after 2.5-dimensional multifocusing correction. Top figure shows uncorrected data that includes offset, inline, and cross-line dip effects. During processing, we need to remove all these effects to align signals to sum up them coherently together. so it requires a new formula to estimate these reflections travel times accurately. This slide shows the new 2.5 dimensional multifocusing reflection travel time formula, which depends on 4 unknown parameters, including theta x, theta y, Rn, and Rnip. The derived formula can explicitly take into account the midpoint dispersion and cross-dip effects. The second term here corrects time shifts associated with the cross-offset to avoid duplication problems. The third and last terms correct move out at the source and receiver locations respectively. We examined the accuracy of the proposed stacking operator on a numerically modeled synthetic dataset. Figure A shows the synthetic velocity model, which includes 3 flat interfaces with different inline and crossline dip components outlined in this table over here. The velocity range was assigned based on prior geological knowledge from the larger lake area. The synthetic seismic data for this model was generated using the finite difference method with the same survey geometry utilized in larger lake seismic profile. Differential evolution optimization algorithm was employed to determine the multifocusing unknown parameters by maximizing the coherency objective function. Figure B shows the resulting stack section along the processing line. For comparison purposes, the interval velocity model along the processing line is transformed from migrated depth domain into the stack time domain, which can be considered as a reference image. Figure C depicts the transformed exact interval velocity model overlaid with the 2.5 dimensional multifocusing stack image. This figure confirms that the proposed method imaged reflections accurately, which are well matched with projected interval velocity model. The result in figure C reveals that our method was able to accurately correct all of the normal, inline dip, and crossline dip move-out effects simultaneously. Also, the proposed method accurately focused reflection at the correct location and produced stacked reflection data with higher vertical resolution. The exact and estimated inline and crossline dips for the synthetic model are summarized in this table. Comparing exact and estimated values demonstrates that the proposed method can extract structural information with good accuracy. In this section, I will present the application of the 2.5 dimensional multifocusing imaging workflow on the Metallurg's larger lake crooked profile, which is located in the Abitibi Greenstone Belt in Canada. This slide shows the geological map of the larger lake transects with the seismic acquisition and processing lines. This transect has a complex geology and is located between the larger Cadillac Deformation Zone in the north and the Lincoln-Nipissing Shear Zone in the south. This table summarizes the acquisition geometry information. The profile length is about 12 kilometers and the source and receiver intervals are about 6 and 13 meters respectively. Also, the CMP interval is exactly 10 meters. The left figure shows the acquisition geometry with the sources in red and receivers in blue. Midpoints are colored by the offset distribution. The solid green and dashed yellow slalom lines represent the processing lines used for the 2.5D multifocusing and conventional workflows respectively. The green processing line has been generated based on the midpoint locations using a low-order polynomial regression approach. The figure B shows the crooked line seismic binning with a constant CMP interval. The midpoints were binned every 10 meters along the slalom line at a maximum radius of 750 meters. We built the super CMP gathers by combining 5 nearby CMP gathers to achieve a high fold coverage. Here, the processing line is colored with the fold number that indicates the number of traces that belong to each super gather. The maximum fold number for the conventional is about 1900, and for the 2.5D multifocusing is about 8500. The close-up figure at top right shows the data points contributing to building a CMP and a super CMP gather. The data points used for the conventional are shown in magenta, and for the multifocusing are shown in magenta plus green. This figure shows an example of the super gather after signal processing and static corrections. This figure demonstrates how challenging it can be to extract signals from this poor quality field data. In this slide, we also compare the pre-processed larger lake data that we used in conventional and in the multifocusing methods. In this example, the super gather, which is shown on the right side, comprises traces from 5 CMP gathers. So super gathering increases the number of folds by a factor of 5 that causes an increasing signal to noise ratio. We developed the 2.5D multifocusing algorithm package code in C using the seismic Unix framework. For efficient implementation of the proposed algorithm, the produced C code package was parallelized using a serial forming technique by shell scripting. Here, after signal processing and binning data, we estimated unknown parameters using the differential evolution global optimization algorithm. Based on prior geological information and conventional images, we set the near surface velocity to 5.5 km per second and the normal wavefront curvature to 0. This decreased the number of unknowns from 4 to 3, including theta x, theta y, and RNIP, which are plotted in the top row here. Figures A and B show estimated inline and crossline dips respectively. Figure C shows the radius of the normal incidence point wavefront curvature, which generally increases with depths. Figure D shows the estimated dip-independent RMS velocity that we calculated using estimated attributes and can be used for further processing steps such as migration. And figure E shows the coherency section. This slide shows the 2.5D multifocusing stack section overlaid on the inline dip, crossline dip, and coherency function sections. Figure A shows the inline dip, which is the apparent dip along the north-south direction. Red and blue colors correspond to positive and negative dips towards south and north respectively. The light bluish color shows horizontal layers. Figure B shows the cross dip, which is the apparent dip along the east-west direction. Red and blue colors correspond to positive and negative dips towards east and west direction respectively. The greenish color shows layers without a cross dip component. In this dataset, the main reflection package has 15 degrees dip to the north and about 10 degrees to the east. Using these two apparent dips, we can estimate true dip, which is valuable information for structural interpretation. In the figure C, the coherency function section overlaid on the stack section and helps us to know which part of the section can be interpreted with more confidence. Here, the hot color indicates high coherent reflections. Here, I'm going to compare the migrated stack sections produced by 2.5 dimensional multifocusing and conventional processing methods. The larger lake seismic data has been processed by different processors from different companies using various conventional processing workflows and strategies. In this presentation, I'm going to show just two of them. The seismic image was produced along the dashed yellow slalom line by applying post-stack Kirchhoff time migration on the NMO stack section. Also, pre-stack Kirchhoff time migration has been applied, which led to the almost same section. This image was generated along the brown straight line by applying the phase shift migration on the NMO and DMO corrected stack section. In addition, a deconvolution filter has been applied to this image. Also, cross-step move-out analysis was applied before migration, which wasn't able to enhance the quality of the resulting image considerably. This image is the result of applying Kirchhoff time migration on the 2.5-dimensional multifocusing stack section derived along the solid green slalom line. Now, I'm just gonna move back and forth to compare these results visually. Note that for each image, the border color corresponds to the color of the processing line. In comparison to the conventional images, our method considerably improved the quality of seismic imaging and alignment of reflection events. In this slide, we plotted the shown images beside each other for comparison purposes. Figures A and B are conventional processing results produced by mentioned two different approaches, and figure C is the result of applying the proposed method. The results show that the 2.5D multifocusing method was able to image new reflections, including dipping and subhorizontal features at the time gate of 1.5 to 3 seconds. Also, several new reflections in the near surface were imaged by new method which are not visible in the conventionally processed seismic sections. Also, the new introduced method focused the conflicting dipping reflections at their correct locations and imaged them clearly compared to the conventional methods. Here, I'm going to compare the main reflections package by cropping and zooming up this portion of the images. Overall, the multifocusing method provided a more clear and coherent image with a higher signal-to-noise ratio than conventional methods. This brings me to the end of my presentation. In summary, we developed a novel generalized multifocusing stacking algorithm for crooked line seismic surveys, which corrects normal, inline, and cross-line dip move-out simultaneously. The performance of the new formulation has been investigated on a synthetic model, which is generated using the same real acquisition geometry used in the larger lake area. Numerical tests show that the new technique can accurately focus the primary reflections at their correct locations and estimate true dips and dip-independent velocities, which can be used for structural interpretation and pre-stack depth imaging. We have presented the application of the proposed method to the larger lake crooked seismic profile. Applying the proposed approach considerably improved the image quality compared to the conventional method. Also, in addition to prominent features, the 2.5D multifocusing method focused new reflections with a high signal-to-noise ratio, which were not imaged by the conventional workflows. And my references are listed here. Finally, I would like to give my special thanks to my supervisors. I thank my fellow graduate students and research associates, particularly Dr. Chiraghi for pre-processing field records. I acknowledge Absolute Imaging for conventional processing of larger lake seismic data. I also appreciate the developers of the Seismic Unix and the 3D finite difference seismic wave simulation open source programs. This research was financially supported by the NSERC Canada First Research Excellence Fund and Mineral Exploration Research Center at Laurentian University. Thank you so much.